This is the second lecture of Lewis electron dot formulas, and we're going to look now at something called resonance or delocalized bonding. And what happens is this applies when a substance cannot be described by a single Lewis structure. So sometimes a substance cannot be described by a single Lewis structure. Here's an example. SO2, sulfur dioxide. Okay. So if we have sulfur dioxide, let's use the rules that we looked at last time to draw the best Lewis structure. So for example, so we have 6 valence electrons with the sulfur, 12 for the oxygen, so we have 18 valence electrons total. After I would challenge you to just pause the video right now and draw a good Lewis structure for this and see what you come up with. You should have something like this as Lewis structure. Now the thing is, what if we were to the issue with this molecule is that we have a double bond going to the oxygen and a single bond going to the other oxygen. What happens with resonance is this. You can't describe the SO2 molecule as just this, with just this Lewis structure. Essentially, you need both this one and this one to describe it. And here's why. And now I haven't just taken this molecule and flipped it over. This oxygen is the same as this oxygen. This oxygen is the same as that oxygen. What we're saying is that you don't actually have a double bond to one oxygen and a single bond to the other, or a single bond to this oxygen and a double bond to the other. What we're saying is that the true structure is an average of the resonance forms. The true structure of the SO2 molecule is an average of these resonance forms. We would say that each form is a contributor, and that the electrons are delocalized. You don't actually have 4 electrons here and 2 electrons here. What you can think of it as is something more like this. Oops, I neglected to put this double bond there. But what you actually have is something more like this. It's almost like you have a bond and a half between the sulfur and the oxygens rather than a double bond. So it's almost like you have a bond and a half rather than a single bond and a double bond. The true structure of the SO2 is an average of these two. You can think of it as being something like this. Most of the time in chemistry, and what you'll see with organic chemistry next year also, is it's good to be able to draw it as one or the other most. Now you might be asking, what evidence do we have that this is the case, that we don't have a single bond or a double bond or a single bond all the time? Well, it turns out that one can measure bond distances with various spectroscopies, and it turns out that the SO bond distances in SO2 are both the same. They're both the same. They both have the same distance. And they're definitely less than a single bond length, but greater than a double bond length. So it's actually sort of like a bond and a half, if you will. It's a resonance between them. The true structure is an average of the resonance forms. In whatever resonance form you have, the arrangements of the atoms must be the same, however, too, just like I have here. So in other words, this oxygen is that oxygen is that oxygen. Now I challenge you to find the resonance form on your own for CO3 2-. There should be 3 resonance forms that you would find for that particular molecule. I'll pause. You might try pausing the video and drawing them out. But what you'll find is the following. Oops. Again, we do this just because it's an ion to remind ourselves that there are 2 extra electrons. For the carbonate anion, the true structure is an average of all of these forms. Each form is a contributor and the electrons are delocalized. So that's resonance delocalized bonding. Always look for resonance structures within the molecules that you may be drawing. There are some molecules that are exceptions to the octet rule when you're drawing Lewis structures. First one are odd electron species. I had mentioned in the last lecture that odd electrons or species are rare, which is true, but they do exist. Here are 2 examples. NO has 11 valence electrons. NO2 has 17 valence electrons. And now I challenge you again to just take a moment, pause the video, write the best Lewis structures for these 2 things. Now, one thing you'll find is that you won't be able to have an octet for the nitrogen or an octet for the nitrogen here. Oops, I meant to put 1 electron on that, not 2. More often than not, again as a rule of thumb, and we'll see why this is the case soon, but more often than not, the least electronegative atom will be the one that has the least electrons on it. So this nitrogen is violating the octet rule. It only has 7 electrons. Why is it that the oxygen wouldn't be the one with the 7 electrons? Well, usually the least electronegative atom will be the one with less electrons. But we'll see exactly why this is the case when we look at formal charge in the future here. Later on in this lecture, in fact. Okay, so odd electron species can violate the octet rule. We can have electron deficient compounds. Atoms with fewer than 4 valence electrons. Is where you see this. For example, beryllium chloride or boron trifluoride. The best Lewis structures for those might look something like this. For boron trifluoride, we would have a Lewis structure like that. the boron and the beryllium each can have fewer than 8 electrons around them because they are atoms that have fewer than 4 valence electrons in them. So things that combine with beryllium, things that combine with boron, things that combine with aluminum might be places where you would see this. Okay, the final exception to the octet rule is the following: the use of D electrons. So the use of D electrons to expand the valence shell. This only happens with elements who are third period or higher. What do I mean by the third period? Well, it's the third row down. So third period or higher. This row cannot do it. This row can do this. Here's an example. 2 examples. I'll give 2 examples. SF6 is one example. And xenon tetrafluoride is another example. When we look at SF6, what we would have is the following as our best Lewis structure. Where we have 8 electrons around each of the fluorines, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons around the sulfur. You might be saying, well, how does this happen? Well, essentially, what happens is sulfur uses its unfilled D electrons. Remember, the third row, we have 3s, 3p electrons, and the 3d electrons also exist. Well, sorry, the 3d orbitals also exist. And they're not being used by sulfur, but they're close in energy to the others. So sulfur uses the D electrons to expand the valence shell, and you can have more than 8 electrons around things third row and higher. Here's an example: xenon tetrafluoride. After drawing this out, what you would find in putting all the electrons and satisfying the octet for this molecule, what you'd find is you still have 4 electrons to place. We're going to place those electrons around the xenon because it can expand its octet. Where is xenon? Xenon's right here. It's in the 5th row. It's in the 3rd row or higher, so it can expand its octet using the D shell, and this would be the best Lewis structure for that. PCl5 is the final example. After drawing the best Lewis structure, you'll find that this satisfies all of the criteria, but we've expanded the octet of the phosphorus. Again, phosphorus is in the 3rd row of the periodic table, and it's expanded its octet. Okay, finally, what we're going to do is look at something called formal charge. Formal charge is quite simply, formal charge can be used as a way to help you decide between 2 Lewis structures that you've used that are alternative, and which one might be the more accurate description or depiction of a Lewis structure or of a molecule. What formal charge is it's a hypothetical charge assigned to each atom. It's a hypothetical charge assigned to each atom in a molecule that's useful in deciding alternative Lewis structures. Formal charge is calculated in the following manner. It's equal to the number of valence electrons around an atom, subtracting off the number of non-bonding electrons, and then subtracting off half of the number of bonding electrons. There are a few things that you need to know about formal charge. The sum of formal charges must equal the charge on the species. So if you have a regular molecule, a neutral molecule, the sum of all the formal charges of the atoms in that molecule must be 0. If you have an ion, it'll be the charge on the ion. The most likely Lewis structure is the one having the lowest magnitudes of formal charges. And then finally, if formal charges do exist, the negative charge should be on the more electronegative atom. No matter what, if you're using this to decide between different Lewis structures, the octet rule will take precedence. So the octet rule does take precedence. Sorry, I spelled that wrong. So you might be able to have two different structures, one where there are no formal charges, but the octet rule is violated. The octet rule is going to take precedence for that, though. Let's look at some examples of using formal charge to decide between two different roughly equivalent structures. Let's take the CO2 molecule. Why would we write it like this rather than like this? And now you start to, so why would we do that? Why is it that the carbon is in the middle and the oxygen is and so on? And you can't say that my rule of thumb is the reason why, is because the rule of thumb comes from the use of formal charges. So let's calculate the formal charges for each of the atoms on these two molecules. Okay, formal charge is, as you remember, so let's calculate it for this oxygen here. It's going to be equal to the number of valence electrons in the oxygen. Oxygen has 1, 2, 3, 4, 5, 6 valence electrons, minus the number of non-bonding electrons. There are 4 non-bonding electrons around that oxygen, 1, 2, 3, 4, minus half of the number of bonding electrons. 1, 2, 3, 4, minus 2. Oh, sorry, minus 4. Our bond. Okay, so our formal charge on this oxygen, 6 minus 4 minus 2, is going to be 0. On the carbon, doing the same thing, we'd end up with 4 valence electrons in the carbon, minus the number of non-bonding electrons, 0, minus half of the number of bonding electrons, which are 8. Again, here we get 4 minus 4 would be 0. So, and then this oxygen, the formal charge on this oxygen, is going to be 0 just like this one. Same calculation. Let's do the calculation for this molecule. So what's the formal charge on the carbon in this molecule? Well, we'd have 4, which is the number of valence electrons in carbon. Carbon atom has 4 valence electrons, 1, 2, 3, 4. Minus 4 non-bonding electrons, minus half the number of bonding electrons, which is 4. So in this case, we have a formal charge of minus 2 for that carbon. This is going to have a formal charge of 0. Let's look at the formal charge on this oxygen. Here, we'd have a formal charge of 6 minus 0 minus half of 8 is going to give us a formal charge of the oxygen of plus 2. So between these two structures, remember, the most likely Lewis structure is the one having the lowest magnitudes of formal charges. I'm not just simply adding the formal charges up and saying, oh, well, they'd be about equivalent because if I add the minus 2 and the plus 2 here and the 0, I get 0 and here. But no, it's looking at the magnitudes of the formal charges on all of these. This is going to be the best structure. Between those two, because it has the lowest magnitude of formal charges. It has 0 in each case. Here's another example of using formal charges to be able to distinguish between two different structures. HCN molecule. Earlier we drew it like this. Which one of those would be better? We drew it like this earlier. Let's use formal charge for each one of these to be able to calculate what it would be. Now, now at this point, I would challenge you to just stop the video, calculate the formal charges for each of the atoms within these two molecules. What you should find is you'll have a formal charge of 0, 0, 0 in this case, but in this case you'll have a formal charge of 0, plus 1, and minus 1 here. So that means the first structure is more likely the better of the two structures between them. You can also use formal charge to distinguish the distribution of electrons. For example, here, if formal charges do exist, the negative charge should be on the more electronegative atom. Let's look at the example here. So for example, we have, as a final example, we have the NO molecule. Which of these two structures would be more likely? Now, I gave you a rule of thumb earlier saying that you should have the least electronegative atom will maybe have an odd number of electrons. But if we look at why that's the case, we get formal charges of 0 and 0 here, minus 1 and plus 1 here. So this one would be the more likely of the structures. So formal so it allows you to look at the distribution of electrons also.